A clock falls toward a black hole, its ticking slowing until it stops completely. This is the edge of a black hole, a place where the universe's own rules break down and time grinds to a halt. We are about to explore the profound mystery of what happens when time slows to a stop at the event horizon. You will gain a new perspective on the nature of reality itself by the end of this journey. We will venture into the most extreme environment known, where the fabric of space-time is stretched to its absolute limit. What would it be like to witness a single moment stretched into eternity? The surface of a black hole is not a solid wall but a river of space itself, flowing inexorably toward an unseen waterfall. This is the event horizon, the final boundary where the universe's current becomes too powerful to resist. According to Einstein's theory of general relativity, this is the point where the escape velocity surpasses the speed of light. Nothing that crosses this line, not even a single photon, can ever come back. Renowned physicist Kip Thorne describes it as a one-way surface, a gravitational point of no return. It is not a physical barrier you could touch. Instead, it is a mathematical boundary defined purely by the black hole's immense mass. Scientists define its size using what is called the Schwarzschild radius, a simple calculation based on that mass. A more massive black hole has a larger event horizon, a wider river flowing toward the cascade. If you were an astronaut falling inward, crossing this threshold would be an uneventful moment. You would feel no sudden jerk, no dramatic tear in the fabric of your ship. Your journey would continue smoothly, pulled by gravity's relentless grip. Yet for anyone watching you from a safe distance, something utterly bizarre would occur. They would see you slow down, your image stretching and reddening until you appear completely frozen, hovering just outside that boundary for all of eternity. This stark difference between your experience and the outside observer's view raises a profound question. What does this tell us about the nature of reality itself, if one person's now can be another person's forever? This thought-provoking paradox, born at the event horizon, is our direct gateway into the strange realm where time itself stretches to a stop. This striking difference in what two observers see is not magic. It is a direct result of gravity's profound ability to reshape the very fabric of time itself. Imagine two perfectly synchronized clocks. If you place one clock deep within a powerful gravitational field, such as near a black hole, and keep the other far away in the emptiness of space, they will gradually fall out of sync. The clock near the immense gravity will begin to tick more slowly. This is gravitational time dilation, a cornerstone of Einstein's theory of general relativity. He showed that mass does not simply pull on objects. It curves the four-dimensional fabric of space-time, and this curvature guides how time itself flows. The stronger the gravity, the more time slows down. We actually account for this effect here on Earth. The global positioning system satellites orbiting high above our planet experience slightly weaker gravity than we do on the surface. Because of this, their onboard clocks run faster by a tiny but measurable amount. If engineers did not constantly correct for this drift, the entire GPS network would become unusable within hours, giving you incorrect directions. This shows that time dilation is not just a theoretical idea. It is a real, engineered part of our modern world. Now, imagine a hypothetical probe on a mission to a black hole. As it approaches the event horizon, it begins sending a regular signal back to us, a steady pulse, once every second from its perspective. But from our distant vantage point, something unusual happens. The intervals between those pulses begin to stretch. 1 second becomes 2, then 10, then 1,000. The signals arrive further and further apart, and the light from the probe reddens dramatically, losing energy. This is not because the probe is malfunctioning. It is because time for the probe is flowing infinitely slower from our point of view. We can even see this mathematically. The equation that describes this slowing is clear. Time for an outside observer is equal to time for the object falling in, divided by the square root of 1 minus a specific fraction. That fraction involves the gravitational constant, the black hole's mass, and the distance from its center. As that distance shrinks toward the event horizon, the denominator of that fraction approaches zero. Dividing by a number approaching zero makes the result grow toward infinity. This is the mathematical heart of the phenomenon. Time dilation becomes infinite. This bending of time challenges everything about our daily experience, where we assume a single, universal now connects us all. The universe, it seems, has no such single clock. That single mathematical fraction approaching zero creates a reality where our film reel of time grinds to a complete halt. The frame freezes. For an observer watching from a safe distance, an object falling toward a black hole does not vanish. It simply slows, its image stretching and dimming until it becomes a permanent, ghostly fossil etched onto the surface of the event horizon. This is the heart of infinite time dilation. The equations tell us that from our vantage point, the object's final approach takes an infinite amount of our time. It never quite crosses, at least not in our timeline. The great physicist Stephen Hawking noted this strange fact, that to an outside viewer, everything that ever fell toward a black hole would appear to be frozen there still, like insects preserved in amber for all of eternity. This bizarre effect is deeply tied to the behavior of light itself. As the object falls, the light it emits or reflects struggles against the immense gravity. Each photon loses energy on its long climb outward, shifting to longer, redder wavelengths. At the very threshold of the horizon, this gravitational redshift becomes infinite. The light loses all its energy, effectively fading to nothing. The object does not disappear in a flash. It dims and reddens until it vanishes from visible sight, and then from every other wavelength, leaving behind only that final, frozen image. But here is the profound paradox. For the astronaut making the fall, this dramatic freeze does not happen. Their clock, from their own perspective, continues to tick forward normally. They would cross the event horizon in a finite amount of their own time, feeling no barrier, no dramatic spike, no sudden stop. This creates two utterly irreconcilable realities. From the outside, the astronaut is forever frozen at the brink. For the astronaut, the brink is a moment they pass through without fanfare, continuing their journey into the black hole's depths. So which perspective is correct? Is the astronaut eternally suspended, or have they already crossed? The resolution lies in understanding that this infinite stretch is what physicists call a coordinate singularity. It is not a true physical barrier within the fabric of spacetime itself. Instead, it is a limitation of our perspective, a consequence of how we, from far away, are forced to measure time and space. The coordinates we use to describe the universe break down at this boundary, creating the illusion of an infinite freeze. This leads to one of the most unsettling puzzles in all of physics, the information paradox. If every object that falls in leaves a frozen, two-dimensional image on the horizon, what happens to all the three-dimensional information it carries? Is that data lost forever, or is it somehow preserved on the surface? The infinite stretch of time at the horizon is not the end of the story. It is a gateway, a profound clue that our understanding of reality is incomplete. And to truly grasp what happens next, we must abandon our safe, distant perspective and take the plunge ourselves. So from the outside, the astronaut is a frozen statue, a permanent monument to a final moment. But what is the reality for the person actually making the fall? For them, the journey inward is not a violent crash into a wall. It is more like floating down a wide, calm river, unaware that you are approaching a waterfall just beyond a bend. According to the principles of general relativity, an astronaut crossing the event horizon would feel nothing special at all at that precise boundary. There is no sudden jolt, no dramatic sign announcing the point of no return. This is a direct consequence of Einstein's equivalence principle, which tells us that the sensation of free fall is indistinguishable from the feeling of weightlessness in deep space. Your own clock continues to tick forward at its usual, familiar rate. Renowned physicist Leonard Susskind emphasizes that for the person falling, time proceeds normally, and they would cross the horizon in a finite amount of their own personal time. The real shift does not come from crossing an invisible line. It emerges later as you journey deeper into the black hole's core. There, the true character of its gravity reveals itself. Gravity's pull is not uniform. It is stronger at your feet than at your head if you are falling feet first. This difference in pull, known as a tidal force, begins to extend your form. Simultaneously, the sides of your body are pressed inward. This extreme process has a vivid name, spaghettification. You would be drawn out into a long, thin stream of particles. The size of the black hole dramatically changes this experience. For a small black hole with an event horizon just a few miles across, the tidal forces are intensely powerful. You would be pulled apart long before you even reach the horizon. But for a supermassive black hole like the one at the center of our own galaxy, the event horizon is millions of miles wide. The gradient of gravity at that boundary is far more gentle. You could cross the event horizon completely unharmed, noticing nothing unusual. In a simulated fall into such a giant, you might not even realize you had passed the point of no return until you were already deep inside. Your journey would continue smoothly, the outside universe shrinking to a brilliant circle of light above you, slowly narrowing into darkness. This creates an impossible-sounding conflict. For us, watching from safety, you are frozen forever at the threshold. For you, that threshold is a moment you pass through without a second thought, continuing your voyage. How can both of these experiences be true? The answer lies not in the physics of the black hole itself, but in the mathematical language we use to describe it. Our distant perspective and the falling astronaut's perspective use different coordinates, different rules for mapping space and time. Both are valid within their own frames of reference, yet they tell two starkly different stories of the same event. To truly resolve this, we must turn to the numbers and the geometry that make sense of this cosmic duality. This profound conflict between two realities, the frozen statue and the smooth fall, is not a flaw in physics. It is a flaw in our perspective, in the very map we use to chart the cosmos. Think of the different ways we can map our own planet. A Mercator projection, like you see on many classroom walls, stretches the polar regions into massive, distorted landmasses. Greenland appears larger than Africa, which it is not. A polar projection centered on the North Pole gives a completely different yet equally valid view of the continents. Neither map is wrong. They are simply different coordinate systems, different lenses for viewing the same spherical Earth. The same is true for black holes. Our initial description, where time seems to stretch toward infinity, relies on what physicists call Schwarzschild coordinates. This is the simplest mathematical framework born from Einstein's equations, and it works perfectly well far from the black hole. But just as the Mercator projection breaks down at the poles, Schwarzschild coordinates break down at the event horizon. They create a mathematical singularity there, a point where the equations produce extreme values, making it seem like time must halt. This is not a real physical barrier. It is an artifact of our chosen map. To see the true, smooth geometry of spacetime, we need a better map. Physicists like Arthur Eddington and David Finkelstein developed coordinate systems that remove this artificial feature. In their description, the event horizon is not a wall of frozen time. It is a one-way membrane, a surface that things can cross in only one direction, inward. The mathematics shows a continuous, uneventful flow across this boundary. An even more complete picture comes from Kruskal-Shekker's coordinates. This is like a perfect global map of the entire black hole spacetime. If you plot the path of an object falling in its world line on this map, you see something remarkable. The line representing the astronaut's journey crosses the event horizon smoothly, without any kinks, loops, or points of infinite time. Their personal clock continues its steady tick, and the horizon is just another point on their voyage. The great Roger Penrose developed a powerful tool called a conformal diagram to visualize all of this in a finite drawing, capturing the infinite expanse of spacetime. These mathematical tools are not just abstract games. They are essential for running accurate simulations of black hole mergers, like those that detected gravitational waves. They teach us a humbling lesson about the limitations of our perception. Our intuition, built on a flat, slow-moving Earth, is a poor guide for the universe's extremes. The reality is that the astronaut does cross the horizon. Our distant view of their frozen image is a persistent illusion, a ghostly echo created by light and gravity working in concert. The seamless connection across the horizon is real, and it is defined by the most fundamental traveler in the cosmos, light itself. Light itself becomes a prisoner at the edge of a black hole. A single photon fired directly outward from just outside the event horizon is like a swimmer trying to climb up a waterfall. It fights against the current of falling space, struggling to make any upward progress. It expends all its energy in the attempt, and as it does, its very nature changes. The light loses frequency and stretches into longer, redder wavelengths. This is the extreme consequence of gravitational redshift. The equation that governs this is stark. The frequency of light we observe is equal to the frequency it was emitted with, multiplied by the square root of 1 minus that same critical fraction we encountered before. As the point of emission gets closer to the horizon, that square root term approaches zero. The observed frequency plummets toward nothing, and the wavelength stretches toward infinity. At the exact boundary, the light is redshifted out of existence. It loses all its energy, fading from view across the entire electromagnetic spectrum, from visible light to X-rays. This is why an object falling toward a black hole doesn't just vanish. It dims and reddens, its final image stretching into a single, infinitely long wavelength until it becomes a permanent, dark fossil on the horizon. There is a subtle but important distinction between light that is emitted from the object itself and light that is merely reflected. A hot, glowing piece of debris falling in emits its own light, which reddens dramatically. A cold, dark rock only reflects light from nearby stars, and that reflected light undergoes the same powerful redshift. Both pathways lead to the same observational silence. This profound manipulation of light is not just a theoretical curiosity. It is a key tool for astronomers. When a star wanders too close to a supermassive black hole, tidal forces can pull it apart into a swirling stream of superheated gas. As this debris spirals inward, the light it emits is stretched and redshifted in a very specific way. By analyzing this light, scientists can infer the presence and properties of the invisible event horizon below, mapping the gravitational well without ever seeing the bottom. The Nobel laureate Roger Penrose took this idea even further, exploring how the spin of a rotating black hole could, through a process called superradiance, actually amplify certain waves of light, extracting rotational energy from the black hole itself. But the ultimate fate of most light is to be trapped. This leads to a deeper, more fundamental question for physics. If light, the universe's ultimate messenger, cannot escape a black hole, what happens to all the information it carries? Every particle, every atom that falls in has a story. Its composition, its energy, its quantum state. According to our classical understanding of gravity, that information is sealed behind the horizon forever. Yet quantum mechanics insists that information can never be truly destroyed. This is the heart of the information paradox, a profound conflict between our two most successful theories of reality. The strange behavior of light at the threshold is the first clue that our map of the cosmos is missing a crucial piece of the puzzle. That final, fading image on the horizon is not just a ghost. It is a clue to one of the most profound puzzles in modern physics, a paradox that touches the very heart of our understanding of reality. Imagine a vast cosmic library containing the complete story of every star, every planet, and every person that ever journeyed into a black hole. Now imagine that library is set on fire. According to the classical rules of general relativity, those books are gone forever, their information irretrievably lost behind the event horizon. But quantum mechanics, the rules governing the very small, insists that this cannot happen. In the quantum world, information is never truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is the black hole information paradox, a direct conflict between our two most successful descriptions of the universe. The great physicist Stephen Hawking brought this conflict into sharp focus. He realized that black holes are not completely black. Due to subtle quantum effects near the event horizon, they slowly emit a faint glow of particles, now known as Hawking radiation. This process causes the black hole to gradually lose mass, shrinking over astronomical timescales until it potentially vanishes entirely. Hawking's initial calculation suggested a startling conclusion. When the black hole finally evaporates, all the information about what journeyed inward would be lost forever, radiating away as completely random, featureless thermal energy. This idea of information loss was so unsettling that it sparked a decades-long debate. If Hawking was correct, we would have to rewrite the foundational laws of quantum mechanics. The conflict is stark. From one perspective, anything that crosses the event horizon is gone, its information held in a singularity. From another, the principles of quantum theory suggest that information must somehow be encoded on the horizon itself, perhaps imprinted on the Hawking radiation that escapes. This led to other startling ideas, like the firewall paradox, which suggested the event horizon might not be a smooth, empty space but a region of intense energy that would transform anything passing through. How can we make sense of this? Think of it like transforming a diary. The pages turn to ash and the words seem lost in the chaotic smoke. But in theory, if you could track every single particle of ash and smoke, every emitted photon of light, you could, with infinite precision, reverse the process and reconstruct every word that was written. The information was not destroyed, it was merely transformed into an incredibly complex state. The real question is whether a black hole does the same thing. Is it the ultimate scrambler of information, or is it the ultimate eraser? Current research, including the holographic principle, suggests a remarkable possibility. All the three-dimensional information about what journeyed into the black hole might be perfectly preserved in a scrambled, two-dimensional code on the event horizon's surface, like a cosmic DVD storing a three-dimensional movie. The resolution of this paradox likely requires a theory of quantum gravity, a framework that can finally unite the world of the very large with the world of the very small. The frozen stretch of time at the horizon is not just a curiosity, it is the starting point for a much deeper journey into the quantum structure of spacetime itself. The chessboard of the cosmos has two conflicting rulebooks. General relativity governs the grand movements of kings and queens across the curved spacetime board, while quantum mechanics dictates the frantic, probabilistic dance of the pawns. To understand what truly happens when time seems to pause at a black hole's edge, we must find a rulebook that works for both games at once. This is the quest for quantum gravity, a theory that would reveal the fabric of spacetime not as a smooth sheet, but as something woven from discrete, vibrating threads. At the event horizon, this new perspective becomes essential. The classical idea of infinite time dilation and a perfectly smooth horizon begins to fray at the edges, revealing what might lie beneath. Physicist Carlo Rovelli, a leading voice in this field, proposes that space and time themselves are granular, composed of tiny, indivisible units. If this is true, then the event horizon cannot be a mathematically perfect surface. It must be a turbulent quantum structure, blurry and dynamic, much like the surface of a boiling sea. This quantum fuzziness could fundamentally alter the fate of anything approaching the brink. Several profound theories attempt to map this unknown territory. String theory, for instance, describes certain black holes not as singularities but as vast, vibrating membranes called D-branes. The information about everything that has crossed into that region is not lost inside, but stored as intricate vibrations on this surface, with the area of the horizon directly corresponding to the amount of information, or entropy, it contains. This is captured by the Bekenstein-Hawking formula, a cornerstone of modern black hole physics that links the horizon's area to its temperature and entropy. Another compelling approach, loop quantum gravity, suggests that the immense density at a black hole's heart might not culminate in a singularity. Instead, the collapse could reverse in a cosmic bounce, transforming the black hole into a white hole, releasing its contents back out into the universe across eons. Then there is the fuzzball proposal, which radically reimagines the black hole's interior. It suggests there is no empty space inside, no sharp horizon, and no singularity. The entire black hole is a giant, tangled ball of quantum strings, a fuzzy region where the familiar concepts of space and time simply break down. In this view, you do not cross a line into emptiness. You merge with a vibrant quantum structure. So how does this quantum tapestry change the paradox of infinite time dilation? Those tiny, frantic fluctuations at the horizon, a seething soup of virtual particles popping in and out of existence, would prevent time from ever grinding to a perfect mathematical halt. From a distant viewer's perspective, an object would still appear to slow dramatically and redshift, but it would not become a true fossil frozen for eternity. The quantum dynamics would eventually process its information, allowing it to effectively cross the horizon and be encoded onto its surface, or be released through Hawking radiation over cosmic timescales. The infinite stretch was always an illusion of an incomplete map. The quantum horizon offers a way out, suggesting that time, while stretched to its absolute limit, never truly stops. It simply transitions into a different form of existence, one where information is preserved, not lost. This bridge between the very large and the very small points toward an even more revolutionary idea about the nature of our universe, the holographic principle. This idea that a black hole's entire interior could be described by a scrambled code on its two-dimensional surface is the holographic principle. It is as if the rich, three-dimensional world we experience is a magnificent hologram projected from a flat, two-dimensional film residing at the universe's edge. The physicists Gerard T. Hooft and Leonard Susskind developed this radical notion from the thermodynamics of black holes. They realized that the maximum amount of information, or entropy, a region of space can contain is not proportional to its volume, as we might assume, but to the surface area of its boundary. For a black hole, that boundary is the event horizon. This means every bit of data that describes the stars, gas, and astronauts that journeyed inward is not lost forever. Instead, it is meticulously painted onto the horizon's surface, with each tiny, fundamental unit of area, a Planck area, acting as a single pixel storing one bit of information. This relationship is captured in the Bekenstein-Hawking entropy formula, a cornerstone of this new physics. The holographic principle found a concrete mathematical home in a discovery known as the AD-SCFT correspondence. This is a powerful duality which suggests that a gravitational theory operating within a certain volume of space is completely equivalent to a quantum field theory without gravity living on its lower dimensional boundary. Think of it like a perfect, self-contained simulation. The frantic quantum dance of particles on a distant, flat screen can generate, through its complex interactions, the entire three-dimensional reality of a world with gravity, stars, and black holes. This provides a stunning resolution to the information paradox. When an object crosses into a black hole, its information is not destroyed. It is immediately transferred and scrambled across the horizon's surface, like a three-dimensional object being instantly compressed into an incredibly detailed, two-dimensional image. An observer traveling inward would experience a continuous, three-dimensional journey, but from the perspective of the universe's fundamental code, they have simply been encoded onto a surface. This challenges our most basic assumptions about reality. We feel we live in a three-dimensional world, but the holographic principle suggests this may be an emergent illusion, a projection from a more fundamental, two-dimensional reality operating at the Planck scale. So what does this mean for the apparent infinite stretching of time at the horizon? If our reality is a holographic projection, then the dramatic slowdown we perceive from the outside is just a feature of that projection. From the higher dimensional perspective of the complete theory, time does not stop at all. The smooth, continuous flow of information across the boundary is preserved. The impression of a frozen image is a consequence of our limited, three-dimensional viewpoint within the projection. These are not just beautiful mathematical ideas. Scientists are actively looking for ways to test them. The fine quantum structure of spacetime predicted by the holographic principle could leave subtle imprints on the light from distant astrophysical events, or even in the data from powerful particle colliders. We are on the verge of potentially observing the fundamental grain of reality itself. The shadow of a black hole is not an empty void, but a silhouette carved from light itself. This is the profound achievement of the Event Horizon Telescope, a global network of radio observatories that function as a single planet-sized eye. By pointing this immense instrument at the supermassive black hole at the heart of galaxy M87, scientists led by figures like Shepard Doleman captured something extraordinary. They imaged a dark central shadow encircled by a brilliant, lopsided ring of light. That shadow is the event horizon signature. It is not the horizon itself, which is unseeable, but the absence of light captured by its immense gravity, a direct testament to the spacetime warping we have been exploring. This glowing ring is the accretion disk, superheated gas spiraling inward at nearly light speed, its light bent and lensed by the black hole's gravitational field. The ring's asymmetry comes from relativistic effects, a real-world validation of Einstein's predictions where light is twisted into a halo around the point of no return. Closer to home, in the center of our own Milky Way, we have a different kind of proof. Astronomers have spent decades tracking the orbits of stars whipping around an invisible, dark point. This point is Sagittarius, a star. By applying the simple laws of orbital motion, they have calculated with stunning precision that an object with over 4 million times the mass of our Sun must be crammed into a region smaller than our solar system. The only thing that fits this description is a supermassive black hole. We are not just theorizing, we are watching the cosmic dance dictated by its immense gravity. Another method involves listening to the universe in X-rays. As gas from a companion star is pulled toward a black hole, it forms a seething, multimillion-degree accretion disk. This hot plasma emits powerful X-rays, and by studying their flickering and spectral lines, we can detect the gravitational redshift and time dilation affecting the light emitted just outside the event horizon. The light struggles to escape, and its stretched-out, lower-energy signature tells us of the immense gravitational well it climbed out of. Perhaps the most dynamic new window into black holes comes not from light, but from ripples in spacetime. The LIGO and Virgo observatories have detected gravitational waves from colliding black holes. These powerful events send tremors through the fabric of the cosmos, and the final moments before the two horizons merge are a direct probe of their dynamics. The specific ring-down signal after the merger carries information about the nature of the final, single horizon, testing whether it behaves as general relativity predicts. But how do we observe the freezing of time itself, an effect that seems to defy observation? We look for its subtle signatures. Some supermassive black holes power quasars, the intensely bright cores of distant galaxies. Their light output can flicker rapidly. By studying the timing of these flickers, astronomers can search for signs that the fluctuations are being stretched and slowed by time dilation as they originate from deep within the gravitational well. It is an indirect echo of the extreme slowing we have discussed. These observations are not just confirming old ideas, they are pushing the boundaries, forcing us to refine our models of what happens at the very edge of reality. Each new piece of data, from a star's wild orbit to a spacetime ripple, is a vote cast for a particular version of the universe, guiding us toward a final theory that can truly explain the edge of time. That shadow we observe is born from a spectacular stellar transition. A star many times more massive than our Sun spends its life in a fragile balance, with the outward push of nuclear fusion holding back the inward crush of its own immense gravity. When such a star finally exhausts its nuclear fuel, this balance shatters. The core collapses in a heartbeat, and the star's outer layers are cast outward in a tremendous release of energy. What remains is a stellar remnant compressed into an unimaginably small point. If the core's mass is greater than a critical threshold, roughly 3 times the mass of our Sun, no known force in the universe can stop the collapse. The matter is drawn within its own Schwarzschild radius, and an event horizon quietly blooms into existence, a new boundary drawn onto the cosmos. This fundamental limit was understood through the pioneering work of astrophysicist Subrahmanyan Chandrasekhar, who calculated the maximum mass a white dwarf star could support before its transformation. Later, the Tolman-Oppenheimer-Volkoff limit defined a similar point of no return for neutron stars. The densest objects made of matter exceed this limit, and gravity wins the final battle, forging a black hole. The formation process directly sculpts the horizon's properties. A black hole born from a single collapsing star will typically have a mass a few times that of our Sun and a horizon only a few miles across. This creates an incredibly steep gravitational well right at its edge, where tidal forces are profound. But there are other pathways. At the dynamic heart of most galaxies, including our own Milky Way, supermassive black holes loom, containing millions or even billions of solar masses. These behemoths likely grew over cosmic time, through the steady accumulation of gas and the merging of smaller black holes, their horizons expanding with each addition. We have even witnessed this directly. The first gravitational wave detection, event GW150914, was the sound of 2 black holes spiraling together and merging. In their final moments, they created a new, larger event horizon, a single boundary that settled into a calm, perfect sphere as described by the No-Hair Theorem. This tells us that a black hole, regardless of how it forms, is defined only by its mass, spin, and electric charge. All other details about the material that created it are sealed away behind the horizon forever. There is also a fascinating, hypothetical third-class primordial black holes. These could have formed not from stellar transitions, but from extreme density fluctuations in the earliest, most energetic moments of the universe. Their horizons would have been microscopic, potentially seeding the growth of the supermassive giants we see today. How does this formation story connect to the stretching of time? A black hole's origin sets its mass and size, which in turn dictates the intensity of time dilation at its surface. The steep slope of a small black hole's gravity well creates a dramatic, rapid slowdown for approaching objects. The gentler slope of a supermassive black hole's well produces a more gradual but equally inescapable time stretch. The horizon is not a physical surface you could touch, but a region of space-time where the escape velocity equals the speed of light. It is a one-way street born from gravity's ultimate expression, and its character is shaped entirely by the nature of its creation. The universe does not build just one kind of black hole. These gravitational giants come in several distinct varieties, each defined by a unique set of cosmic properties. The simplest form is the Schwarzschild black hole, a perfect sphere of darkness defined only by its mass. It is the idealized drain in our cosmic sink, a non-rotating, uncharged vacuum. But most black holes in the universe are likely anything but simple. They spin, and that spin transforms them entirely. When a massive star collapses, it conserves the angular momentum of its predecessor, often resulting in a black hole rotating at a significant fraction of the speed of light. This rotation is described by the Kerr metric, a solution to Einstein's equations discovered by physicist Roy Kerr. A Kerr black hole is not a static sphere. Its rotation drags the very fabric of spacetime around with it, like a spoon stirring a thick fluid. This creates a region outside the event horizon called the ergosphere, a squashed sphere where nothing can remain stationary. The dragging of spacetime is so powerful that any object within the ergosphere is forced to move in the direction of the black hole's spin. This phenomenon, known as frame dragging, has a direct and fascinating effect on time. The relentless whirl of spacetime makes time itself slow down even more dramatically for an outside observer than it would at a non-rotating black hole of the same mass. The event horizon itself changes shape under rotation, becoming oblate, wider at the equator and flattened at the poles like a spinning drop of water. We can also imagine a charged black hole, known as a Reissner-Nordström black hole, though these are thought to be rare in nature as they would quickly neutralize by attracting opposite charges from their environment. In this case, the electric charge adds a repulsive component to the gravity, which can theoretically create a more complex horizon structure with both an outer and an inner horizon. The most realistic model combines all these properties, a charged, rotating Kerr-Newman black hole, where mass, spin, and charge all work together to define the landscape of spacetime around it. Consider the famous stellar black hole Cygnus X1. Observations of its accretion disk, the superheated gas spiraling into it, show clear signs of intense frame dragging. The disk is warped and tilted, its inner regions whipping around at incredible speeds, a direct observational clue that we are not looking at a simple Schwarzschild drain. So how does this diversity change the experience of time slowing at the edge? For a rotating black hole, the point of infinite redshift, where light loses all its energy, is not at the event horizon itself, but at a different surface called the static limit, which lies at the edge of the ergosphere. An object could potentially cross the static limit and enter the ergosphere, and with a powerful enough rocket, it could still escape. But within this whirling region, time is stretched in a more complex way, twisted by the vortex of spinning space. The journey toward the true event horizon becomes a spiral, corkscrewing along with the flow of spacetime. This rich variety shows that the simple picture of a perfect freeze is just the beginning. The specific architecture of a black hole, sculpted by its mass, spin, and charge, dictates the precise nature of the gravitational environment and the strange flow of time on its threshold. And this leads to an inevitable, deeper question. If the outside is so complex, what strange geometry lies within the horizon itself? Beyond that final threshold lies a realm where the universe inverts its own rules. You have passed the point of no return, and now the interior of the black hole unfolds. Here, the roles of space and time are not just bent, they are completely swapped. In the world outside, you can choose to move forward or backward in space, but you are always carried relentlessly forward in time. Inside the horizon, this familiar logic is undone. The direction toward the central singularity is no longer a choice in space, it becomes your future. You cannot avoid moving toward it, just as you cannot avoid moving toward tomorrow out here. The radial direction itself becomes time-like. Every possible path, every trajectory your ship could take, now points inward toward the center. It is as if the entire universe inside the horizon is collapsing, and you are a part of that collapse, swept along by the very flow of space-time. The great physicist Kip Thorne described this as a region where the predictions of general relativity reach their breaking point, signaling the need for a deeper quantum theory of gravity. The geometry inside is a one-way street to a destination that defies our understanding. At the heart of this inward rush lies the singularity, a point of infinite density where the curvature of space-time becomes extreme. This is not merely a very dense object, it is a place where the very concepts of space and time cease to have any meaning. Our equations produce infinities, a clear sign that our map of reality has failed. The journey toward this center is not necessarily a smooth descent. Some theoretical models, like the Becquerel conjecture, suggest that as you approach the singularity, the gravitational forces could become chaotic. The orderly pull you felt earlier might break down into a turbulent, unpredictable churning, stretching and compressing matter in wild oscillations. There is a critical distinction in the types of singularities predicted. A space-like singularity is one that lies in your future, an inevitable event you will encounter. This is what general relativity suggests for a Schwarzschild black hole. A time-like singularity, theoretically possible in a rotating Kerr black hole, could be avoidable, a place you could circle around without necessarily hitting, though other forces would likely still overwhelm you. But perhaps the most profound feature of the black hole interior is its complete causal disconnection from the universe you left behind. In the elegant lines of a Penrose diagram, the interior is a separate region, a box from which no line, no signal, no influence can ever cross back into the external universe. The event horizon is a one-way causal boundary. You can receive information from your past from the outside, but you can never send anything back. The light from the stars you once knew continues to rain down upon you, a final, fading image of a cosmos you can no longer affect. This raises a deep mystery about the nature of time and space. If the flow of time outside becomes a direction in space inside, what does that say about the fundamental structure of our reality? Is this inversion a unique feature of these gravitational phenomena, or a hidden property of the cosmos that only reveals itself under the most extreme conditions? Venturing into this conceptual abyss where physics as we know it ends, prepares us to ask the ultimate question about the final fate of these cosmic giants. A block of ice does not melt all at once. It sublimates, vanishing particle by particle into the air over time. In the profound stillness surrounding a black hole, a similar, almost imperceptible process is underway. The void is not completely empty. Stephen Hawking's revolutionary insight revealed that black holes are not the eternal prisons we once thought. They slowly evaporate, fading away over timescales so vast they defy human comprehension. This evaporation is driven by the restless quantum sea at the very edge of reality. Even in what we call a vacuum, pairs of virtual particles constantly flicker into existence, a particle and its antiparticle partner, borrowing energy from the universe only to merge and return it an instant later. This quantum dance usually leaves no trace, but at the event horizon, the intense gravity can separate these pairs. One particle crosses the boundary, while the other, left without its partner, cannot merge. It becomes real, drawing a tiny amount of energy from the black hole's gravitational field and escaping as radiation. This is Hawking radiation. The mathematics shows this radiation has a thermal spectrum, a perfect glow whose temperature is inversely related to the black hole's mass. A stellar mass black hole is so cold, only a fraction of a degree above absolute zero, that it absorbs more cosmic background radiation than it emits. But as it loses mass, it shrinks and its temperature rises. The evaporation accelerates. A black hole with the mass of our Sun would take 10 to the 67th years to vanish, a number so large it outlasts all the stars in the universe. But a tiny, hypothetical primordial black hole, formed in the universe's first moments, could be reaching its end right now. Its final moments would be a brilliant flash of high-energy gamma rays, a signature we could potentially detect. This gradual loss of mass means the event horizon is always subtly shrinking. How does this quantum whisper affect the dramatic slowing of time we perceive from the outside? The eternal freeze frame begins to thaw. The infinite stretch of time is revealed as an approximation, a classical illusion that breaks down when quantum effects are considered. The horizon is not a static wall. It is a dynamic quantum surface, and its slow evaporation ensures that nothing is truly frozen forever. This leads to the most profound consequence of all, the information paradox. If a black hole evaporates completely, radiating only random heat, what happens to the detailed information about every star and atom that ever crossed its boundary? Is the story of those objects lost forever, violating a fundamental law of quantum physics? Hawking's discovery did not just give black holes a finite lifetime. It tied their ultimate fate to the deepest questions about the nature of information and reality, suggesting that even the darkest objects in the cosmos are subject to the subtle, unstoppable flow of time. These silent anchors are woven into the very fabric of the cosmos. At the heart of nearly every large galaxy, including our own Milky Way, a supermassive black hole resides, not as a destructive vacuum, but as a gravitational heart that profoundly shapes its home. The orbits of stars whipping around our galactic center, meticulously tracked for decades by astronomers like Andrea Ghez, reveal the undeniable presence of Sagittarius, a star. This invisible titan, holding over 4 million solar masses within its grasp, acts as a central pivot for the galaxy's grand rotation, but its influence extends far beyond mere gravity. When these cosmic giants feed, they transform into the most powerful engines in the universe. Vast rivers of gas spiral inward, forming a seething, luminous disk of superheated plasma. This accretion process can release so much energy that it outshines the entire galaxy, blazing as a quasar or an active galactic nucleus. The Hubble Space Telescope has captured stunning images of these brilliant beacons at the core of distant island universes. This colossal energy output creates a powerful feedback loop. The intense radiation and hurricane-like particle winds pouring from the black hole can push away surrounding gas, the very raw material needed to form new stars. In this way, a feeding black hole can effectively slow star formation in its galaxy, regulating its own growth and the galactic life cycle. In other cases, the black hole's influence can be more constructive. Colossal jets of plasma, launched from the poles of the accretion disk and stretching for thousands of light years, can press into distant clouds of interstellar gas. The shockwaves from these encounters can compress the gas, triggering the birth of new stars in a spectacular display of creative influence. This intricate dance suggests a deep, co-evolutionary bond. Astronomers have found a remarkable correlation between the mass of a galaxy's central black hole and the properties of its surrounding stellar bulge. It is as if the galaxy and its dark heart grew up together, their fates intertwined across billions of years. When galaxies interact and merge, their central black holes eventually spiral together, an event we can now detect through gravitational waves. These cosmic unions redistribute immense amounts of energy and gas, reshaping the new galactic structure entirely. So how does the extreme slowing of time at the event horizon connect to this grand galactic story? While the time dilation itself is a local effect, the black hole's existence as a stable, long-lived anchor is what allows it to exert such a persistent influence over cosmic timescales. The same gravity that alters time at its edge also holds vast star clusters in orbit, governing the motion of billions of stars over the lifetime of the universe. This role as a cosmic architect, a sculptor of galaxies on the largest scales, invites us to consider a deeper question about the nature of time itself. If a black hole can simultaneously be a place where time changes and a catalyst for galactic evolution that unfolds over eons, what does that tell us about the relationship between our fleeting human moment and the vast, patient clockwork of the cosmos? A moment frozen at the event horizon is not a paused video waiting for a play button. It is a permanent fixture, a single note held for all of eternity. This striking image challenges the very way we perceive time's flow. We experience life as a constant progression from a fixed past through a fleeting present into an uncertain future. But the physics of black holes suggests this may be a profound illusion, a local experience rather than a universal truth. Philosophers of physics like Tim Maudlin ask whether time is a fundamental river moving through the cosmos or a quality that emerges from a deeper, timeless reality. The extreme time dilation at a black hole's edge tests these ideas to their absolute limit. When we say time stops there, what do we actually mean? It does not stop in an absolute cosmic sense. It stops only from the perspective of a distant observer. For the person falling in, time continues its steady rhythm. This is the relativity of simultaneity in its most extreme form. There is no single, universal now that connects all points in the universe. Your now and my now are not necessarily the same. This realization echoes ancient philosophical puzzles. The Greek philosopher Zeno presented his famous paradoxes, arguing that a flying arrow must be motionless at every individual instant, and that to cross a room you must first cross half the remaining distance, then half again, in an infinite series that can never be completed. The still figure at the horizon is a modern, gravitational version of Zeno's arrow, seemingly held in an endless sequence of moments just outside the finish line. Modern physics resolves Zeno's paradox with the mathematics of calculus, which allows us to sum an infinite number of ever smaller steps to reach a finite destination. Yet at the black hole, the outside observer never sees that destination reached. This leads to the eternalist or block universe view supported by relativity. In this model, the past, present, and future all exist with equal reality. The universe is a static, four-dimensional block where our conscious experience simply moves along a predetermined track. If this is true, what becomes of free will? Are our choices an illusion, our lives a story already written in the cosmic record? Considering time's flexibility at these extremes can be deeply thought-provoking. To conceive of eternity is to look into a depth that our minds, shaped for short-term survival, are not equipped to fully grasp. It can make our brief, human-scale concerns feel small, or on the other hand, make every passing moment feel infinitely precious. This is not a call to existential worry, but an invitation to wonder. The bridge between the physics of black holes and the philosophy of time reminds us that our intuitive reality is a small window into a much stranger cosmos. Our effort to understand a still moment at the edge of a black hole is ultimately a struggle to understand ourselves and our place within the grand, unfolding story of existence. That deep shadow in Renaissance art, a place of darkness and deep feeling, was once our closest cultural parallel to a black hole. Long before we understood the physics, humanity looked into the void and filled it with its most profound concerns. These cosmic objects have traveled through our collective imagination, transforming from symbols of pure apprehension into subjects of deep fascination. The 18th century gave us the first scientific hint with John Mitchell's dark stars, objects so massive that light could not escape. But it was in the 20th century, as Einstein's theories took hold, that the black hole truly entered our cultural awareness. Writers of imaginative fiction were among the first to explore their narrative potential, crafting stories where these gravitational giants were gateways to other realms or challenges for distant travelers. This evolution in storytelling mirrors our own growing understanding, moving from uncertainty toward a genuine desire for knowledge. A pivotal moment in this journey was Carl Sagan's Cosmos series. With his unparalleled gift for communication, he translated the complex science of relativity and event horizons into a language of wonder that millions could embrace. He did not just explain the facts, he framed them within the grand human story of exploration, making the cosmos feel approachable. This set the stage for a new era of scientific storytelling in popular media. The film Interstellar stands as a landmark achievement in this tradition. Physicist Kip Thorne worked closely with the filmmakers to ensure the visual representation of the black hole gargantua was not just artistically stunning but scientifically thoughtful. The result was a glowing, warped accretion disk that became an iconic image, bringing the concept of gravitational lensing and time dilation to life with dramatic clarity. The scene where the crew experiences years passing in moments on a watery world near the black hole is a powerful, emotional illustration of a complex theory. It makes the stretching of time feel tangible, something that touches human lives and relationships. This cultural interplay is not limited to film. In music, the band Muse titled a song Supermassive Black Hole, using the phenomenon as a metaphor for a powerful emotional draw or a significant personal change. Visual artists create stunning digital renderings that explore the calm, awe-inspiring, and beautiful geometries of space-time warps. Literature uses the black hole as a setting for deep inquiry, a place where characters face the great mysteries of existence and the nature of reality. These artistic interpretations are far more than simple entertainment. They provide a crucial human context for abstract scientific concepts. When we see a character grappling with the consequences of time dilation, or hear a song that uses a black hole as a symbol for a personal journey, we connect with the science on an emotional level. It stops being a set of distant equations and starts to feel like a part of our shared human experience. This cultural lens directly shapes how the public understands an idea as unfamiliar as time slowing. It becomes less a technical paradox and more a profound moment of reflection, a quiet space that invites us to consider our place in the universe. The ongoing conversation between science and art is vital for welcoming the cosmos, transforming what was once a mysterious shadow into a frontier of endless wonder. A virtual reality headset can transport you from your living room directly to the edge of a black hole. You look down and see the accretion disk warping around the central shadow, a river of light twisted into a brilliant halo. As you begin your descent, the entire sky behind you compresses into a single, shrinking circle of blue, while the black hole's gravitational lensing stretches the starlight into unrecognizable arcs. This is not science fiction, it is an educational simulation, a powerful tool designed to visualize the unseeable. Scientists at NASA, a Goddard Space Flight Center, use the precise mathematics of general relativity to build these digital environments, rendering the warping of spacetime with remarkable accuracy. Astrophysicist Andrew Hamilton has developed interactive journeys that let you fly toward a black hole, experiencing the optical distortions and the one-way flow across the event horizon in a way equations alone cannot convey. The software must handle profound challenges like simulating the infinite gravitational redshift where the light from your virtual ship would dim and redden until it effectively vanishes from view, a fade to black coded directly from Einstein's field equations. Beyond specialized research tools, accessible software like Universe Sandbox allows anyone to play cosmic architect, placing black holes in simulated star systems and watching their gravitational influence unfold in real time. Online courses from institutions like Caltech and MIT open these concepts to a global classroom, while Planetarium shows Project Immersive, all-encompassing visuals that make you feel as if you are adrift in the void. The film Interstellar offered a landmark example of this synergy. The black hole gargantua was not an artist's guess. It was a visual rendering born from a collaboration between director Christopher Nolan and physicist Kip Thorne. The resulting image of a glowing, spinning disk of light, warped by gravitational lensing into a perfect halo, became an iconic and scientifically thoughtful depiction. So how do these immersive experiences change our understanding? They translate abstract theoretical debates into sensory reality. The profound philosophical conflict between the frozen image and the smooth fall becomes an experience you can navigate, making the paradox feel intuitive rather than purely intellectual. By making the extreme physics of black holes tangible, these tools do more than just teach. They inspire a sense of direct encounter, transforming the most mysterious objects in the cosmos from distant ideas into places we can, in a virtual sense, begin to explore for ourselves. This profound simplicity is the ultimate cosmic eraser. A black hole formed from the dynamic transition of a star or the powerful merging of two others does not hold onto the intricate details of its origin. It forgets the complex patterns of the star's internal fusion, the detailed chemistry of its planetary system, even the form of any traveler who may have entered. According to the No-Hair Theorem, a black hole is described by only three numbers: its mass, its electric charge, and its spin. Everything else, all the information that made the original material unique, is smoothed away, leaving a perfectly simple gravitational surface. The physicist John Archibald Wheeler, who helped popularize the term black hole, also introduced this elegant idea, observing that black holes have no hair. They are the universe's ultimate minimalists. This principle comes directly from the solutions to Einstein's equations of general relativity. The mathematics reveals that any irregularities or asymmetries in the forming object are carried away as gravitational waves during its creation. The final, quiet state is captured by the Kerr-Newman metric for a rotating, charged black hole, a solution that depends only on those three quantities. It is a bit like pressing a piece of clay into a perfectly shaped mold. No matter how detailed the clay's original shape, the final impression emerges with the same smooth, defined contours. This is why scientists can describe every possible black hole with such a straightforward set of parameters. If you were to find two black holes with the same mass, spin, and charge, you would have no way to distinguish between them, even if one began as a single star and the other from the collective material of an entire galaxy cluster. Their individual pasts are no longer visible to the outside universe, yet this beautiful simplicity creates a deep puzzle when we consider quantum mechanics. Quantum theory holds that information about a system's prior condition can never be truly erased, only rearranged. The No-Hair Theorem, in its pure classical form, seems to suggest the opposite, that information is permanently sealed away. This is the information paradox appearing in another form. The theorem does have its boundaries, especially when we explore ideas beyond standard general relativity. In some models involving new fields, like certain scalar fields, black holes might develop very subtle features, holding faint external traces of what lies within. These are not actual strands, but additional qualities that could make one black hole minutely different from another. What does this cosmic forgetting tell us about reality? The No-Hair Theorem shows us a universe where vast complexity can be distilled into breathtaking simplicity. It hints that at the most fundamental level, the cosmos might operate with a surprisingly small set of rules, and that the rich diversity we observe could arise from just a few basic elements. This elegant minimalism stands in sharp contrast to the vibrant, information-rich activity we see at the horizon, from the bending of light to the release of gravitational waves during a merger. The quiet, simple object and its lively, detailed surroundings are two aspects of the same profound mystery, inviting us to consider whether true simplicity is the foundation upon which all complexity is built. That silent dance of two whales creates waves felt across the entire ocean. Deep in the cosmos, a similar, invisible dance unfolds as two black holes orbit one another, their immense gravity churning the fabric of spacetime itself. These are not waves of water, but ripples in the very geometry of the universe, gravitational waves that stretch and squeeze everything in their path as they travel outward at light speed. For decades, these waves were only a prediction of Einstein's theory, but today, observatories like LIGO and Virgo have given us ears to listen. The pioneering work of physicists like Rainer Weiss, who earned a Nobel Prize for his contributions, made this new sense possible. The story these waves tell is one of inevitable attraction. As two black holes spiral around each other, they lose energy by radiating these space-time ripples. This loss of energy draws them ever closer, tightening their orbit in a final, accelerating dance. The frequency and amplitude of the waves increase, building to a crescendo. Then, in a fraction of a second, their two distinct event horizons touch and merge, settling into a single, larger horizon that quivers like a struck bell. This entire cosmic event is encoded in the gravitational wave signal, which has three clear phases. The long in-spiral phase tells us about the masses of the black holes and the shape of their orbit. The merger phase reveals the moment the two horizons become one. Finally, the ring-down phase is the sound of the new, single black hole shaking off its imperfections and settling into a calm, perfect sphere, as described by the No-Hair Theorem. The first direct detection of these waves, event GW150914, was a landmark moment. It confirmed a century-old prediction and provided a direct glimpse into the dynamics of event horizons in their most active state. By analyzing the specific frequencies and patterns in the signal, scientists could not only confirm the existence of the black holes, but also calculate their masses and spins with stunning precision before and after the merger. How does this connect to the strange slowing of time at a single horizon? The gravitational waves are generated by the motion of the black holes through space-time, a space-time that is already profoundly warped and time-dilated near their horizons. The waves themselves carry an imprint of that extreme environment, a record of how gravity behaves at its most intense. This new window of gravitational wave astronomy allows us to study black holes not as static objects, but as dynamic, moving entities, testing the limits of general relativity in ways light-based astronomy never could. The event horizon can be modeled as a stretched elastic sheet, a surface that ripples and resists any attempt to disturb its perfect calm. This is the membrane paradigm, a brilliant conceptual tool developed by physicists including Kip Thorne and Richard Price. Rather than wrestling with the full, complex geometry of spacetime, this approach treats the horizon as a two-dimensional surface endowed with effective physical properties. It possesses an effective surface gravity directly linked through quantum mechanics to the black hole's temperature. It also has an effective viscosity, a kind of internal friction that dampens any vibrations. This turns the abstract boundary into something we can almost feel, a dynamic skin that interacts with the universe outside. The power of this model shines when we simulate how a black hole interacts with surrounding matter. As gas from an accretion disk spirals toward the horizon, the membrane paradigm allows us to calculate the stresses and strains on this conceptual surface. The resulting friction and shear can be modeled to understand how energy is dissipated, which in turn helps explain the launching of immense jets of plasma from the black hole's poles. It provides a surprisingly accurate, albeit simplified, mathematical picture. The stretching of an object by tidal forces, for instance, can be elegantly described as a stress applied to this elastic membrane, which then responds according to its effective properties. This fluid dynamic analogy is profound, painting the horizon as a kind of dissipative layer, a cosmic fluid that absorbs energy and information. But how does this simplified view help us grasp the enigma of time apparently stopping at the edge? The membrane paradigm cleverly sidesteps the infinite complexity of the full gravitational field. By projecting all the physics onto a two-dimensional surface, it gives us a handle on what happens there without forcing us to confront the mathematical singularity that represents the frozen star from an outside perspective. In this model, the infinite redshift and time dilation are encoded in the membrane's properties. An object approaching the horizon appears to slow and fade not because time has stopped in an absolute sense, but because its interaction with this dynamic surface becomes infinitely protracted from our distant point of view. It is a computational fiction that yields profoundly correct answers, making the unintuitive somewhat manageable. Yet this very strength is also its limitation. The membrane is a mathematical scaffold, not a physical reality. It works beautifully for describing interactions from the outside, but it tells us nothing about what lies within the horizon or the genuine experience of passing through it. The paradigm offers no insight into the smooth transition felt by an astronaut, a reality confirmed by more complete coordinate systems. It is a tool for external engineers, not internal explorers. Ultimately, this intuitive framework serves as a vital stepping stone. It prepares the mind for more abstract, but potentially more fundamental, ideas like the holographic principle, suggesting that treating a boundary as the source of all physical reality might not be so far-fetched after all. These ancient black holes are cosmic fossils, born not from the end of stars but from the intense beginnings of the universe itself. While stellar black holes mark a star's final chapter, primordial black holes are relics from the very start, possibly forming in the first fleeting moments after the Big Bang. In that incredibly dense and hot early environment, small regions of space might have collapsed under their own gravity, sparked by powerful density shifts during the universe's rapid expansion or its dramatic early transitions. This process could have created black holes across a vast range of sizes, from as small as an asteroid to many times the mass of our Sun. Their size is key as it shapes their destiny and how we might discover them. The rate at which a black hole loses energy through Hawking radiation depends on its mass. A very small, asteroid-mass primordial black hole would release its energy extremely fast, potentially closing its life in a bright flash of gamma rays we might observe. A larger one with the mass of a planet or star could still be moving through the galaxy today, completely dark and unseen. This opens a captivating possibility. Could these ancient, hidden objects be part of the mysterious dark matter that binds galaxies together? While current observations, like the detailed patterns in the cosmic microwave background, set boundaries on how much dark matter they could represent, the search continues. Scientists look for them through subtle gravitational influences. If a primordial black hole moved between us and a distant star, its gravity would bend light, briefly brightening the star in what is known as a microlensing event. Surveys watching millions of stars have recorded some interesting brightening events, though not yet the clear population that would prove they are common. Another approach involves tuning into the high-frequency gravitational waves that very small primordial black holes might emit as they fade, a signal future observatories could one day detect. Picture one of these primordial travelers, an object with the mass of Mars yet squeezed to the size of a small stone, entering our solar system. We would not see it directly, but its gravity would gently pull on the planets, creating slight, mysterious shifts in their paths, a faint trace of its journey. How would the profound slowing of time near its tiny boundary appear from our view? From our perspective, the moment that boundary formed in the early cosmos would be drawn out over billions of years, a single instant from the dawn of time resonating into the present. Exploring these potential relics links the physics of black holes directly to the conditions of the Big Bang, offering a special view into the highest energies and the earliest moments of all we know. This early universe perspective naturally widens our gaze to consider even more speculative ideas, where black holes might be portals not only to singularities, but to entire other cosmic realms. A black hole could be the universe's most profound doorway. Beyond the event horizon and the intense journey inward, some interpretations of Einstein's own equations suggest a startling possibility: a tunnel through space-time itself. This theoretical passage is known as a wormhole or an Einstein-Rosen bridge, a solution that mathematically connects two distant points or even entirely separate cosmic realms. In this breathtaking view, the central point at a black hole's heart might not be a final destination, but a bridge to another domain. Theoretical physicist Lee Smolin has taken this idea even further, proposing a form of cosmic natural selection where every black hole gives rise to a new universe, complete with its own, slightly adjusted set of physical laws and constants. Our own universe, with its delicate balance for life, could be one in a long lineage of cosmic offspring, refined by the success of its star-forming black holes. These are the speculative edges of cosmology where physics meets philosophy. The mathematics of general relativity does not forbid such wormholes, but it does present a profound challenge. For such a tunnel to remain stable and passable, it would need to be held open by a form of matter with negative energy density, something often called exotic matter. While we see hints of such effects in quantum phenomena like the Casimir effect, the sheer amount needed to sustain a cosmic shortcut is far beyond anything we can currently conceive. This is the crucial divide between a mathematical solution and a physical reality. In the serene realm of equations, wormholes are elegant possibilities. In the tangible universe, they are likely to collapse instantly or perhaps never form at all. This has not stopped them from becoming a staple of imaginative fiction, where they serve as perfect devices for interstellar travel. Yet in real science, they remain profound theoretical curiosities, pushing us to ask deeper questions. What would happen to time and causality if such a link were possible? If you entered a black hole here and emerged in another reality, would you have traveled backward or forward in time? Could you send a message to your own past? The laws of physics as we know them strive to prevent such paradoxes, which is one reason many physicists suspect nature forbids traversable wormholes entirely. The true answer likely lies in a theory of quantum gravity, which would describe the foam-like, fluctuating structure of spacetime at the smallest scales. In that dynamic quantum landscape, tiny wormholes might constantly flicker in and out of existence, and the emergence of a new universe within a black hole could be a fundamental process. These ideas stretch our imagination to its absolute limit, transforming black holes from simple gravitational traps into potential architects of a vast, perhaps infinite, multiverse. They compel us to consider not just the fate of what falls in, but the incredible possibility of what lies beyond. A silent fleet of telescopes now turns its gaze toward the dark heart of our galaxy, not as individual instruments but as one colossal eye. The next generation of the Event Horizon Telescope aims to do more than capture a single, historic image of Sagittarius, a star. Its goal is to create a movie, a real-time video showing the turbulent dance of light and plasma as it swirls around the event horizon. This is not science fiction. It is the immediate future of observational astronomy, a coordinated global effort to watch the edge of time itself in motion. By linking radio dishes across the planet and even into space, this enhanced array will achieve a resolution so sharp it could, from Earth, read a newspaper on the moon. This incredible precision will allow scientists to test specific predictions of general relativity with unprecedented detail, watching how the black hole's shadow wobbles and shifts, directly probing the space-time vortex caused by its spin. Above the distorting veil of our atmosphere, new eyes are opening. The James Webb Space Telescope uses its powerful infrared vision to study the dynamic weather of accretion flows around distant black holes. It observes how vast clouds of gas and dust are drawn inward, heated to incredible temperatures, and then flung away by powerful winds, mapping the complex ecology that feeds these cosmic giants. Meanwhile, the planned LISA mission, a space-based gravitational wave observatory, will listen for an entirely different kind of signal. While current detectors hear the final, frantic seconds of black hole collisions, LISA will tune into the low-frequency hum of their entire cosmic history, from the slow, billion-year in-spiral of supermassive black holes to the subtle tremors of smaller objects falling into them. This multi-messenger approach, combining light, gravitational waves, and even the potential detection of neutrinos, builds a three-dimensional picture of these enigmatic objects. On Earth, the exploration continues in unexpected places. In laboratories, physicists are creating analog black holes using supercooled Bose-Einstein condensates or flowing water. In these controlled systems, sound waves play the role of light, caught by a fluid flow that moves faster than sound, creating an effective acoustic horizon. By studying how these sonic ripples behave, researchers can test ideas about Hawking radiation and horizon dynamics in a tabletop experiment, offering tangible insights into the quantum nature that may surround a real event horizon. The European-led Black Hole CAM project exemplifies this comprehensive strategy. By combining advanced telescope arrays with sophisticated mathematical models, it seeks to peel back the layers of Sagittarius, a star, moving from a blurry image to a detailed portrait that reveals the precise spin of the black hole and the complex structure of its magnetic fields. How will these technological leaps resolve the mystery of time at the edge? They will transform the infinite stretch from a theoretical abstraction into a measurable phenomenon. By tracking individual clumps of gas in their final orbits, we may directly observe the extreme time dilation and gravitational redshift, watching as their light struggles to escape, slowing and reddening before our instruments. The future of black hole science is a collaborative, global endeavor, one that promises to test the limits of our knowledge and perhaps reveal the point where Einstein's universe meets the quantum world. This journey into the unknown is not just for scientists. It is a human story of curiosity, and each new discovery invites everyone to share in the wonder of exploring the final frontier of space and time. A black hole is not a cosmic vacuum cleaner endlessly pulling in everything across the galaxy. This common image is one of the most persistent myths in all of astronomy. In reality, a black hole follows the same law of gravity as any other massive object. Its pull weakens with distance, just like the sun's gravity holds the planets in orbit without drawing them in. If our sun were somehow replaced by a black hole of equal mass, Earth would not be pulled inward. Our planet would continue to orbit just as it does now, simply circling a point of darkness instead of a ball of light. The real shift only begins if you venture extremely close, crossing into the territory where the escape velocity exceeds the speed of light. This distinction is vital for accurate science communication, a point often shared by educators like Neil deGrasse Tyson, who work to translate complex ideas into clear public understanding. Another fundamental misunderstanding lies in the name itself. A black hole is not an actual hole in the fabric of space. It is a region of space defined by an immense amount of mass compressed into an incredibly small volume. The event horizon is the boundary of this region, not a physical surface you could touch. Think of it as the point on a map marking the edge of a waterfall, not the waterfall itself. The real source of the phenomenon is the singularity at the center, the point of extreme density where our known laws of physics reach their limit. The horizon is simply the point of no return surrounding it. This leads to another clarification about the experience of crossing that boundary. The journey is not necessarily a dramatic, destructive event. For a small stellar black hole, tidal forces would indeed stretch an object apart long before it reached the horizon. But for a supermassive black hole with an event horizon millions of miles wide, the gravitational gradient is so gentle that you could cross it without even noticing. There is no sudden jolt, no dramatic pull. You simply pass from one region of spacetime to another, from which there is no outward path. The illusion of time freezing at the horizon is also widely misinterpreted. We have explored how, from a distant observer's perspective, an object appears to slow down and redden, its image seemingly preserved forever at the edge. But this infinite stretch is a feature of that specific viewpoint, a consequence of the light's long struggle to escape. For the person or probe actually making the passage, time does not stop. Their clock continues to tick normally. They cross the horizon in a finite amount of their own personal time, feeling no great shift at that precise moment. The freeze frame is an illusion for the audience, not the actor on the stage. Even the permanence of black holes is a concept we must refine. They are not eternal prisons. Through the quantum process of Hawking radiation, black holes slowly lose mass, fading over cosmic timescales. A small black hole could vanish in a brilliant release of energy, while a supermassive one would take longer than the current age of the universe to diminish. Many people also believe these objects are exceedingly rare. The truth is quite the opposite. Most large galaxies, including our own Milky Way, host a supermassive black hole at their center. They are a fundamental part of galactic architecture. Clearing up these confusions does more than just correct facts. It fosters a deeper, more informed appreciation for the science. When we move beyond the simplistic idea of a destructive cosmic vacuum, we can begin to see black holes for what they truly are: powerful gravitational engines that shape the evolution of galaxies and provide unique laboratories for testing the laws of physics. This educational effort is an ethical consideration as well, ensuring that as we explore the most extreme environments in the cosmos, the public conversation is built on a foundation of wonder rooted in reality, not on fear born from fiction. Our growing mastery over these cosmic forces carries a profound weight of responsibility. The same knowledge that allows us to map a black hole's shadow could one day lead us to harness its immense gravitational energy, or to confront a previously unseen presence drifting into our celestial neighborhood. Philosophers like Nick Bostrom encourage us to consider these far-reaching questions, asking what duties we hold as a species when we unlock fundamental powers. While the creation of artificial black holes in particle accelerators remains a remote theoretical possibility, the broader ethical landscape is very real. Every mission we launch to study these objects, from advanced space telescopes to future interstellar probes, carries an environmental footprint we must thoughtfully manage. The cultural responsibility is equally significant. Discoveries about the edge of time should not belong to a single nation or group, but must be shared through inclusive, global dialogue, fostering a collective sense of wonder and ownership over our cosmic heritage. This research, while driven by pure curiosity, consistently generates technological gifts that benefit everyone. the precise algorithms developed to sharpen the Event Horizon Telescope's image now improve medical brain scans. The need for international collaboration in such vast projects builds diplomatic bridges and sets a precedent for peacefully exploring the final frontier. It demands we create thoughtful policies for space exploration long before we face a scenario like a potential signal from another world near a black hole. The sheer time dilation involved would make a simple conversation stretch across millennia, a humbling reminder that our actions could echo for eons. The awe we feel when contemplating a frozen moment at the event horizon is not just scientific, it is deeply existential, forcing us to reflect on our fleeting place in an immense cosmos and our role as its conscious witnesses. This holistic perspective, blending science with ethics and wonder, completes our journey, reminding us that the greatest discovery may not be how the universe works, but how we choose to explore it with wisdom and care. Our journey has taken us from the event horizon's silent pull to the faint quantum glow that hints at its eventual fade. We have seen how time itself stretches thin at that final boundary, a relative experience that depends entirely on who is watching. This relativity of time dilation, the persistent puzzle of the information paradox, and the deep cultural meaning we find in these dark objects are not just scientific footnotes. They are profound reminders that black holes are far more than destructive voids. They are cosmic workshops, extreme environments where we test the very laws of physics and glimpse the hidden rules governing time, space, and existence. Carl Sagan's words resonate deeply here. Somewhere, something incredible is waiting to be known. Let this exploration be a spark, an invitation to keep looking up and questioning the nature of everything around you. How does the idea that time can slow to a near stop reshape your own sense of reality, of a single moment's place in the vast cosmos? If this adventure to the edge of understanding has ignited your curiosity, consider subscribing for more journeys into the heart of space's greatest puzzles. We would love to hear your thoughts on black holes in the comments below. Thank you for joining this voyage where every moment stretched to its limit holds infinite possibilities